Hello folks, I'm Vijit, an engineer by profession. It is the knowledge that was imparted to my siblings and I, mainly by our father, made us professionals serving the society. I decided that the society at large must benefit from what I know, and the videos that I have put out are dedicated to the memory of my late father. Now let us proceed with the subject matter.
A question raised in the derivation of area of a triangle. As a response to the previous video on Heron's formula and the calculation of the area of triangle, I received the following question. In calculating the area of the triangle using first principles, you named a part of the side of the triangle divided by the perpendicular dropped from the opposite vertex as the unknown variable. Was it not possible to use the length of the perpendicular as the unknown variable, as it is the quantity that needs determining? Let me answer your question as follows. Let us take the numerical example of the last video. The sides of the triangle are BC equals lowercase a equals 14, CA equals lowercase b equals 13, AB equals lowercase c equals 15. The foot of the perpendicular was dropped from A to BC is D. Refreshing our memory, in the last video we named CD equals x and applied Pythagoras theorem on triangles ABD and ACD, resulting in the following equations. AB squared equals AD squared plus BD squared, labeled as 1. AC squared equals AD squared plus CD squared, labeled as 2. Now subtracting equation 2 from equation 1 results in AB squared minus AC squared is equal to BD squared minus CD squared, labeled as 3. Substituting the respective values, we obtain 15 squared minus 13 squared is equal to 14 minus x whole thing squared minus x squared. Upon solving for x, the value of it was 5. Substituting the values for x in equation 2, 13 squared is equal to AD squared plus 5 squared, resulted in the determination of AD is equal to 12, hence the area. Why not name AD as H and then solve for H? Let me purposely repeat the question raised. Why not name AD as H and then solve for H? Yes, it is possible, and let us now apply the Pythagoras theorem on the respective triangles again. AB squared is equal to AD squared plus BD squared, labeled as equation 1. AC squared is equal to AD squared plus CD squared, labeled as equation 2. Changing the subject of the equations, we obtain the first one becomes BD squared is equal to AB squared minus AD squared, labeled as equation 3. Equation 2 now becomes CD squared is equal to AC squared minus AD squared. Hence, taking the square roots of the equations 3 and 4, resulting BD is equal to square root of AB squared minus AD squared. CD is equal to square root of AC squared minus AD squared. It therefore follows that BC is equal to BD plus DC, which is equal to square root of AB squared minus AD squared plus square root of AC squared minus AD squared. Substituting the values, we obtain as follows. 14 is equal to square root of 15 squared minus h squared plus square root of 13 squared minus h squared. Now, the task is to solve for h. Obviously, it is not a simple first degree equation, but one involving radicals. Let us face the challenge of solving the equation below. 14 is equal to square root of 15 squared minus h squared plus square root of 13 squared minus h squared. Now we know that a squared minus b squared is equal to a plus b into a minus b. Substitute the following to a and b to the identity above. Namely, a equals square root of 15 squared minus h squared and b is equal to square root of 13 squared minus h squared. Therefore, a squared minus b squared is equal to the square of the square root of 15 squared minus h squared minus square of the square root of 13 squared minus h squared, which in turn is equal to 15 squared minus h squared minus 13 squared minus h squared, which is equal to 15 squared minus 13 squared equals 56. Therefore, 56 is equal to the product of square root of 15 squared minus h squared plus square root of 13 squared minus h squared into 15 squared minus h squared minus square root of 13 squared minus h squared. Note the value of the product. Square root of 15 squared minus h squared plus square root of 13 squared minus h squared and square root of 15 squared minus h squared minus square root of 13 squared minus h squared is equal to 56. However, square root of 15 squared minus h squared plus square root of 13 squared minus h squared is equal to 14. Hence, 14 times square root of 15 squared minus h squared minus square root of 13 squared minus h squared is equal to 56. Thus, consequently, square root of 15 squared minus h squared minus square root of 13 squared minus h squared is equal to 4. We have now derived two equations consisting of surds. Square root of 15 squared minus h squared plus square root of 13 squared minus h squared equals 14, labeled as equation A. Square root of 15 squared minus h squared minus square root of 13 squared minus h squared equals 4, labeled as equation B. Let us now add both sides of the equations labeled A and B, resulting in 2 times square root of 15 squared minus h squared equals 14 plus 4, which is equal to 18. Hence, square root of 15 squared minus h squared is equal to 9. Further simplification leads to h squared equals 144, finally obtaining h equals 12. Since AD equals simple h equals 12 and BC equals 14, we can apply the standard rule to compute the area. That is, area equals half times base times height. And that comes to half times 14 times 12 equals 84. Hence the area is 84 square units. I did not use the method described in this video in the previous one, as the solution of the radical equation derived is complicated. I will now derive the calculation of the height for the general case. In doing so, I will be skipping some of the steps so that the length of this video will not be long. It should be clear by now that the radical equation that needs to be solved is A equals square root of c squared minus h squared plus square root of b squared minus h squared. However, the product square root of c squared minus h squared plus square root of b squared minus h squared and square root of c squared minus h squared minus square root of b squared minus h squared is equal to c squared minus b squared. Hence, square root of c squared minus h squared minus square root of b squared minus h squared is equal to c squared minus b squared divided by a. As shown in the specific case, the two radical equations can be added and simplified to get square root of c squared minus h squared is equal to half of c squared minus b squared divided by a plus a. Rearranging the term results in h squared is equal to c squared minus 1/4 that of c squared minus b squared divided by a plus a whole thing squared. Further rearranging, we get 4a squared c squared minus a squared plus c squared minus b squared whole thing squared divided by 4a squared. Upon further simplifying and taking the fact that the differences of squares into consideration, the net result is a plus c plus b into a plus c minus b into b minus a plus c into b plus a minus c divided by 4a squared. Let us rewrite the value of h squared in the cyclic order. H squared is equal to a plus b plus c times a plus b minus c times b plus c minus a times c plus a minus b whole thing divided by 4a squared. Let us note the following, and I will be brief here. Sum of the lengths of all sides is twice the semiperimeter. Hence, a plus b plus c is equal to 2s. A plus b minus c is equal to twice s minus c. B plus c minus a is equal to twice s minus a. And c plus a minus b is equal to twice of s minus b. Hence, h squared finally becomes 4 into s minus a into s minus b into s minus c divided by a squared. Noting that AD squared is equal to 4 times S minus A into S minus B into S minus C divided by A squared results in AD squared into A squared divided by 4 is equal to S into S minus A into S minus B into S minus C. However, the area of the triangle is equal to A times AD divided by 2. Hence, the square of the area denoted by delta squared is equal to AD squared into A squared divided by 4, which is equal to S into S minus A into S minus B into S minus C. Hence, delta is equal to the square root of S into S minus A into S minus B into S minus C, which is the Heron's formula. Finally, we have obtained Heron's formula from first principles. Observations. In answering the question, yes, it is possible to make the height as the variable. The result is the solution of a radical equation and not a simple first-degree equation. The solution becomes complicated. It takes more time to solve in this method than in the previous video. Taking more time means a disadvantage when answering an exam. Nevertheless, this is an opportunity to learn about the solution of certain type of radical equations. Now I conclude my observations.
I do hope that you have got to know something which you have never thought much before. If you do appreciate, I am happy, as it bears fruit to my objective. All questions can be mailed to me in the given address. Thank you.